So, spherification is a newer type of culinary process and it makes use of sodium alginate and some type of calcium solution. It's usually calcium chloride and it basically forms a liquid into spheres. So, what would commonly happen, or the most basic process, is you would add a small percentage of sodium alginate into a juice, and then you would take a bowl of water and add a small percentage of calcium chloride into the water, and you would drop the juice into the water and it would basically form like a thin membrane around the juice, so it would look like a sphere. So a common food that is used or made by this process is the frozen yogurt toppings that are shaped like little spheres that burst in your mouth. So before I go into explaining what diffusion is, which is basically an important process in spherification, it's important to know what a polymer, cross-linking, and a gelatin are. So basically a polymer is some type of substance that's mainly made of like the same type of unit or molecule. And as you can see, there's a picture of it there, of an example of one. And cross-linking is how this polymer is sticking together. It's by covalent bonding. And a gelatin, as you can see, is a virtually colorless and tasteless water-soluble protein prepared from collagen, which is a type of protein and used commonly in food preparation. And as you can see, there's a picture of gelatins there, which basically looks like jello. So in this slide, I'm just going to explain a little bit more about what polymers and cross-linking are. So basically, I like to think of a polymer as one big huge supermolecule, because if you look at a polymer chain, it's basically made of the same molecule throughout, which I also explained in the last slide, but it's just important to know that. And these molecules are held together by cross-links. They're usually covalent, but they can be ionic. And the weak intermolecular forces among these polymer molecules attract them towards one another, which is why these polymer chains are so big and huge and made of the same molecule. And these polymer molecules aren't able to slide over each other easily, which is also why it's such a long chain, and this is why polymers usually have a high melting point. And in terms of molecular gastronomy, the calcium chloride ions cause these long chain alginate polymers to become cross-linked, forming a gel. So when you're dropping this like juice and alginate solution into the water and calcium chloride solution, the calcium chloride ions are causing these alginate polymers to become cross-linked, and this is why the liquid forms into like sort of a gel or a sphere. By the way, guys, I put the rock here because he's one really big super dude, just like a polymer is one really big super huge molecule. So you guys probably already know what diffusion is from like bio and chem class, but it's basically the intermingling of substances by the natural movement of their particles. That's the most basic definition of it. So this relates to spherification because the diffusion occurs when the cross-linking calcium ion, like we talked about before, diffuses from an outer reservoir and into the alginate solution. So this is basically how the like membrane's created around the sphere. And the thickness of the shell or membrane depends on the length of time that the drops are submerged in the alginate or calcium bath. So as you can see in the picture, that yellow or orangey part, it represents the membrane, or like the shell. And as the time is increasing, the shell is getting thicker and thicker. And this is especially true in direct spherification. So as you can see in the picture also, like the longer that diffusion gets to occur, the thicker the membrane is going to be. So the first type of spherification I'm going to explain is direct spherification, and this is the most general or basic type of spherification. I've kind of been explaining this process all along. All the types of spherification are very similar. They have minor differences, but basically in this process, the spheres that are made have a very thin membrane that easily break into your mouth when you bite into it. So that's one of the big pluses of this process. One of the big negatives, though, is that even after you take the spheres out of the calcium bath, they will continue to gelify, meaning that the membrane will continue to get larger and larger until the point where there's no juice inside and it's just pure gel. And so because of this, they're best served immediately, so you can't really preserve the spheres. The gelling agent in this process is in the juice and not the bath, so the alginate will be in the juice. And in this process, the membrane goes inward, so once again, as time goes on, the membrane will continue to get larger and larger from within. And lastly, the pH has to be above 3.6 or it might not work. And this basically refers to the juice. The pH has to be above 3.6. It can't be too acidic. And there are things you can do to get around this, but some people like to use reverse spherification because it has less negatives and it's kind of more versatile, and I'll explain that in the next slide. So the next type of spherification is reverse spherification, and this is instead of submerging a liquid with sodium alginate into a calcium bath, you're basically going to do the opposite as like what you would do in direct spherification. So you're going to submerge a liquid with calcium into a sodium alginate bath instead. And this actually makes it more versatile because you can use liquids with calcium, and that's something you couldn't do in direct spherification. So you can use things like milk, yogurt, or like cheese and stuff like that. And in this process, jellification can be stopped. And this is another positive of this process because in direct spherification, the membrane would continue to gellify until it was there was no longer liquid inside of it. But in this process, that doesn't happen, so that's a good thing. That means you can also like save the spheres for later. The only problem with this process is that the membrane does still tend to be thicker, and also there's a thin layer of gel on the membrane. So the last type of spherification we're going to talk about is frozen reverse spherification, and this is basically the same thing as reverse spherification. You're still going to have the calcium solution or calcium mixture that you're going to place in the sodium alginate bath. The only difference is that when you make this calcium mixture, you're going to freeze it by putting it into a mold, and then after it freezes, that's when you place it into the sodium alginate bath. And the plus side to this process is that because you don't have to shape the mixture with a spoon, you can save any frustration it might take or any time it might take to try and make the shape with the spoon, and you get whatever shape you want by putting it into the mold. So these next few slides will be about emulsions, and a basic definition of what an emulsion is that it's a fine dispersion of small droplets of one liquid in another in which it is not soluble. So another definition, or something that's kind of easier to understand, is that it's a mixture of two or more liquids that are normally immiscible, which basically means unmixable or unblendable. A very common type of emulsion is oil and water, and there's some listed below, and in the next few slides we're just going to go a little bit deeper into what an emulsion is. So in the last slide, there was a list of common food emulsions, but in terms of molecular gastronomy, a common type of emulsion is a foam. So in molecular gastronomy, emulsification is a technique used to incorporate and stabilize air bubbles in a liquid mixture. So a liquid can trap air bubbles and turn it into a foam. And technically, this isn't a type of emulsion because if you think about it, if you look at a foam, such as the picture above, the air bubbles are trapped within the foam, and they're not actually mixed in. And this is why it's an emulsion. And a common way to trap air bubbles in a liquid is by whisking it, but the air bubbles will escape in a short amount of time. So if you think about like whisking eggs or something, you might develop a foam at the top, but it'll quickly go away. Another device you can use to do this is an immersion blender. There are a lot of different types of devices to do this, but that's just one common one. Also, egg and milk protein, bread starch, gelatin, cream fat, and lecithin, not sure if I pronounced that right, are common emulsifiers. And in these products, their molecules act as barriers between the air and water. So commonly, if you were going to try to make a foam, you would use these common like items to try and make the foam. So the next few slides are going to be about gels, and a gel is basically a solid jelly-like material that can have properties ranging from soft and weak to hard and tough. So a more technical definition would be that they're defined as a substantially dilute cross-linked system, and they exhibit no flow in the steady state. So some examples are obviously like jelly, butter would be an example, and shoe polish would also be an example. Another type of gel is called a hydrogel, and the definition is obviously on the side. I don't want to make this video too long, so it's right there for you guys. So some other types of gels are elastic gels and non-elastic gels, and I'm not going to go into this too much because the definitions are on the slides, but basically when an elastic gel is heated and it'll form a dry mass, and then if a liquid is put into that dry mass, it'll go into its original form. And also elastic gels are lyophilic, and they also show imbibition, and non-elastic gels don't show that. So lastly, I'm going to explain monitors tools to use with spherification. So I'm not going to go into much detail because I don't want to make this too long again, but syringes, spherification spoons, and silicone tubings are all used in direct and reverse spherification, and molds are mainly only used in frozen reverse spherification. And for whipping siphons, I'm not sure if I said that right, but they're used with making foams. So this is just my works cited page. Again, guys, I'm sorry this is super long, and I hope you guys found this helpful.